Hi, this YouTube video will just give you a very simple introduction to how we can carry out some very simple analyses in the mixed models options in SPSS. All it's doing is looking at some of the analyses we carried out before, a pair t-test and an independent samples t-test, about how we can do this in this options to get used to the new dialog boxes. So here we have some data that we looked at eons ago, which was sit-ups I think before and after a particular intervention, and then we have the last column which shows ID, the patient identifier. So we notice this is what's in wide format, so each row represents a case. To use the mixed option in SPSS, mixed models option, we have to have it in long format. So to do that we have to convert it from wide to long. My previous YouTube video talked about doing that, and I've already done it, so we'll just go and look at see what it looks like, the result. So here's the result in long format, where we have now two rows for each subject. Each represents one of the values, results for pre and post, pre and post, pre and post. So now we can actually use this option, analyze mixed models. And what we want to do is I'm going to show you how you would carry out an independent samples t-test using these dialog boxes. Remember, this is totally ridiculous because we know that the time 2 value is highly dependent upon the time 1 value for each individual, but we'll ignore that for now and assume they're two independent groups. So the first thing when we choose this linear mixed models option is get this dialog box up here. We can totally ignore it this time and click continue. Then here we know we have a dependent variable, and we know that is the result. And the factor, well, we know that is the time. We're classing each time we take the result at a particular level of this factor here. And what we've got to do is say that this factor is what's known as a fixed factor. So we click on fixed, and we select it there and move it over to the model, so it's actually put in our model. Click continue. And then we just want to say what statistics we need. Click on their statistics and choose parameter estimates. Say continue and click OK. And here are the results. We get several tables which I'll talk about later on, but the most important thing is if we look down here we get a time equals 1 parameter estimate, and the p-value associated with that is 0.0623. The actual value is minus 2.62. So if we actually look at the results I did earlier on, these results I did earlier on just actually carrying out independent samples t-test as we do normally, and we noticed that we've got a simultaneous value there 0.623, exactly the same, and a t-value of minus 0.503, which is identical. Now we know that was stupid, so let's do something a little more sensible now and carry out a paired samples t-test using these dialog boxes. To carry out the paired t-test equivalent in the mixed models menu option, we use our same data set that we have in the long format. We just go to analyze, mixed models, linear, and this time we put something into this first dialog box which is really concerned with defining repeated measures. So first of all choose ID as a subjects, which we know that, and then the repeated measure is actually time. We put that in a repeated box, and I'll talk about this in my notes, but for now just do it. Choose unstructured. I'll mention this at the end what this does, and click continue. And then we know our output is still the result, a dependent variable, and the factor is time, and we need to define this again as a fixed factor, so we go into the fixed factor option and say add. Once we've moved it over, click continue. And statistics, we make sure we've chosen the parameter estimates as we won't see anything. OK, continue, and then just say OK to get the results. Ignoring the first few tables, we'll move down to the bottom of the output, and we notice that two tables of interest at the moment are the estimates of fixed effects and the estimates of covariance parameters. If we look at the estimates of fixed effects, notice we have a row for time equals 1, and we've got a t-value of minus 2.049. The significance value, that's a p-value of 0.08. Now if we compare that with what I had before when I carried out a paired t-test, we notice we had there t of minus 2.049 and a p-value of 0.08, which is exactly the same. Also notice some other things about the output from the paired t-test that initially look very different from what we have when we do the mixed measures equivalent, but they're not actually. Here we have paired sample statistics from our paired sample t-test, and we have for the pre-group we have a standard deviation of 10.402. Remember, the standard deviation is just the square root of variance, so if we say 10.402 times by 10.402, we'll get the variance of that, which is actually 108.2. Similarly, 10.466, if we square that value, we get 109, roughly. So if we look back at our output here, we see that's exactly what we've got, 109 there and 108 there. Where it says 1, 1, 2, 1 and 2, 2, that's talking about rows and columns. So the first number refers to the row, the second number refers to the column. And I'll just show you how that works again in an output here. Here we have those three values shown in the form of a column. We've got the first column is time 1 and the second column is time 2. So we've got, as you see, 1, 1 is equal to 108, and that's the variance for our pre's. And then we've got post, which is the variance for the post values. And then we've got this value where it takes pre and post, which is the covariance, how much they covary. And even go further, if you remember that the covariance is just the unstandardized correlation. So if we take here, the correlation is equal to the covariance divided by the standard deviation of both the variables. And the standard deviation, as I said, is the square root of the variance. So we know what the variance is from that table above. If we take the covariance, which we've got from that table, take both the variances, and we do that little equation, and we get a value of 0.939. 0.939. If we go back to the original paired t-test output, we have a correlation of 0.940, which is the same as 0.939. So you may ask, why have we done all that when we've just got the same results that we've got from a simple independent samples t-test and also a paired samples t-test? Well, that is because I just wanted to show you the very basics. What we've done there is created two models and thought about them. We can now look at the way we could actually create another model with the repeated measures, and this is to do with that covariance matrix which I skimmed over at the beginning. Here we have a table that lists 5 types of covariance matrix. And what does this thing mean? Well, a covariance matrix is just telling you a way of setting up the values for the repeated measures. So if we look at a scaled identity covariance matrix for repeated measures, it's saying that the variance at each time point is the same. So for our pre and post, we'd expect them to have same variance, the same degree of spread of scores. And at each kind of time, we also can look at the correlation between those values, because we know they're not independent, we know they're correlated somehow. So we can say, do we expect them to be correlated or don't we? And if we expect them to be correlated, do we expect these correlations to change over each of the time points, or are they the same? So for our first, this scaled matrix, we're saying that the variance each time point is the same, and the correlation doesn't exist, they're completely independent, and that was actually equivalent to doing an independent samples t-test if we'd used that scaled identity covariance structure. But if you remember, we didn't. We chose the unstructured covariance, which is the third one, and the unstructured covariance matrix fits their data when it assumes that the variance each time point is different and the correlation in each pairs of the times is different as well, but that's a bit trivial in our case because we only have 2 time points, so we can't really compare correlations. But if you remember, the actual variance for both pre and post were pretty much the same, so why go for this unstructured thing when it means that we're going to work out a parameter estimate for each time point for the variance? Why not go for something that just says it's a constant variance for all the time points that we've got in our data set? And to do that, we can just use this compound symmetry one here, which says that the variance is a constant for each of our time points, and also the correlation stays the same for all the time points, which might as well say means we've only got 2 time points and it doesn't make any difference. So we'll rerun our analysis now with compound symmetry as the way of modelling our data over time. Back in SPSS, it couldn't be simpler. We just go to Analyse, Mixed Models again, Linear, and it's still got the results we chose from last time. And all we do is change the repeated covariance type now to compound symmetry. Click Continue, and we see exactly the same thing as we had as before. And we'll just look at this statistics. We also ask for tests of covariance parameters here. Continue. OK. And now if you notice in our output we've got a slightly different set of tables. Here it says compound symmetry, whereas before it said unstructured. And you'll notice here the number of parameters we used there was 5 for the previous model, because we had to use 1 for each of the variances. Now, if we look here, we're not using as many. We've reduced it by 1 because we only need to work out 1 variance value, which equals both pre and posts. So if we look down here, we've got this -2 restricted log likelihood again, and remember that's a measure of how close the data fit the model, so we'll be using that in a minute. And then we've got our parameter values here again, and this is exactly the same, -2.049 with a p-value of 0.08, so there's nothing changed there. But we have got now what's known as covariance parameters, which tells us the estimate of the covariance value as well. So the important thing is we're going to compare this model that assumed equal variance over time and equal covariance rather over time and equal variance for both time points with that which it didn't assume that before. So we've got here a -2 log likelihood, restricted log likelihood of 94.529 with 4 degrees of freedom from there. From previous model we've got -2 restricted log likelihood of 94.526 with the all important 5 degrees of freedom. So how do we compare these two values? How do we do this? Well, looking at my notes, we used a thing called the likelihood ratio test, which compares the values of these -2 restricted log likelihoods. And what we do is subtract the value of the less complex model from that of the more complex one. And then remember the two values were 94.526 and 94.529. And if we take the one from the other, we get 0.003. And we also compare the degrees of freedom. Well, we know degrees of freedom were 5 and 4, so it's 5 minus 4, which leaves us with 1 degree of freedom. And we know that follows a chi-square distribution. So we've got a value of 0.003 with 1 degree of freedom, and we can use R to find out what the p-value is with that chi-square. And there's the graph. I'll show you very simply how I did that. If we go to R Commander, we just go to Distributions, Continuous Distributions, chi-square, plot chi-square. We plot in chi-square of degrees of freedom 1. Let's have a look at that. There is our chi-square distribution from our commander. Then if we just type in grab line, as I've done before, vertical equals 0.003, adds it to our graph there, and we want the value, as we know, 1 wanted to the right, so it's 1 minus p chi-square bracket 0.003 with 1 degree of freedom. And there it is, 0.956. And if we look here, we can actually add a little bit of text, which I've done. Let's copy and paste that. And it adds the text for us saying that. So, what do we conclude from that value of 0.956, that p-value? Well, we conclude that we would obtain two models displaying a similar degree of fit, or one less similar, 96 times in 100, given that they come from the same population. It's a standard interpretation of the p-value. And considering the hypothesis testing approach, you know, the one that everyone loves with the critical value, which I'm not so keen on, we could say that means it's greater than 1 in 20, that's a 0.05 level. We accept this model. We accept there is no difference in the degree of fitness between the two models we've looked at. But remember, one uses one more degree of freedom than the other, and it's always best to choose the model that uses least degree of freedom, because what we want is the most parsimonious model. That means the simplest model. Degrees of freedom are valuable things, and we don't want to use them up with all the parameters. So the least parameters describe our model efficiently is the best thing. So I would go for the simpler model with our compound symmetry covariance matrix, which is saying that we consider that the variances for the two time periods are the same, the pre-post values are the same variance values, and correlation doesn't change over time, which is ridiculous because we've only got two values. But it's the simplest model. Bye.